Alright, so in this video, we're going to talk about forces on planar surfaces, and the key here is that they're submerged. Alright, and what this means is they're underwater, clearly. So, really, these forces stem from hydrostatic pressure. All right, so we're going to look at something that looks something like this. All right, so here's our solid surface. All right, remember these three lines here mean it's a liquid interface. All right, we're going to call this angle here alpha. All right, we'll have a pressure of the atmosphere up here. All right, and important to note here, this point, I'm going to do this in green so we can really see it. This point in green here, and this arrow going down, all right, that's my origin in the y direction on my surface. So if I looked, I'm sort of doing a side view here. I'm going to draw an eyeball right here, and if I was looking at that from that eyeball's point of view, right, that surface might have some arbitrary shape like this, okay? And here is that J again, and here would be the X on the surface, all right? So that's one point of reference, all right? Now, there could be another frame of reference, obviously, which is in the direction of gravity. So remember, gravity would be going this way, so we could say that. All right, and we could have, at some point here, all right, let me move that out a little bit. Oop. All right. At some point, let's say here, we could have some distance h. Okay. Now it's important that h is this distance from the top of the surface, okay, to my surface here, and that it translates to a little sliver, all right, on this arbitrary shaped surface here. So this is sort of this surface here, right? And so that there's this little sliver here where that is at some depth h below the surface. And that depth below the surface could also be expressed, right? This position here could be expressed as some distance y, right? To the same thing, okay? So if I was to say to you, what is the force, the dF, the little bit of force on this little area, you would say, well, assuming it's hydrostatic condition, there's some pressure at that area, all right, and then the area itself, all right, and this is this little area, we'll call this dA, okay? So there would be this pressure times dA. All right. Now, what's that pressure? Well, because we're smart, we remember the last video. Due to hydrostatic pressure, we can say that as PATM plus rho GH times dA. So we could break that up a little bit and say that that is PATM times dA plus rho GH times dA. All right, and then that's dF. And then if I want to say, well, what's the total force on this whole surface? Well, that would be the integral of that little incremental force, and that would be the integral of PATM dA plus the integral of rho GH dA, and that would be the integral over my surface, and let's call this surface S. So this would be a surface integral, like that. Okay? So that the total force on that surface would be the surface integral PATM dA plus the surface integral rho GH dA. Okay. Now, in the frame of reference of J and Y and X, and let's call this I rather than X. So here's I, and here's J. In the frame of reference of I and J, all right, we can actually say something about h. And why? We could say that h is actually equivalent to y sine of alpha. All right? Because this distance here is my y distance, right? And we could use SOHCAHTOA to show that. Okay? So if I come back over here, I can say that my force total is equal to the integral PATM dA. Well, PATM is a constant, right? So this is the integral PATM times the total area of my surface, which we'll just call A. Okay? Plus the integral over my surface of rho g. And instead of h, I'm going to write y sine alpha dA. All right, and this is equivalent to PATM times A plus rho g sine alpha, okay, times the integral of y dA. Now, if I have an arbitrary shape, like this one up here, I can say that y of its centroid is actually equal to 1 over a, the integral over the surface of y dA. All right? Right there. Okay? So, I can rewrite now that the total force is going to be PATM times A plus rho g times sine alpha, all right, times the position of the centroid times the area. Okay? And that's because, going back to our previous slide, all right, that's because when we look at this slide, all right, because of this integral, we can replace this. And then y of the centroid is the position of the centroid, all right? And typically, we would say that if I come back to my picture here, maybe the centroid is located right there. And so this position here is my y of the centroid. It's the position of the centroid, all right, and it's defined by that integral. And you guys should know what a centroid is. Okay? So I can now say, all right, the force, in red here, the force total equals PATM plus rho g y centroid sine alpha times my area of my shape. Now, let's think about this. Going back to our picture, all right, going back to our picture, all right, if this is YC, and we know that H equals Y sine alpha, all right, so here's YC, and we know this, and we know this, all right, then this YC sine alpha is equivalent to HC, which is the depth of the centroid, okay, under the surface, which means that this is equivalent to PATM plus rho GHC times A. And this formula here, this is the pressure at the centroid of my shape. All right? So the force on a planar surface, in words, is the pressure at its centroid times its area. All right, in words. Or simply the force is equal to pressure at the centroid times the area. All right, now remember this pressure at the centroid we currently say is PATM plus rho GHC. All right, but there's a little bit more we can do here. There's a little bit more we can think about. So if we go back to our basic idea, here is our shape, our surface, here's our solid surface. All right, this was PATM over here. If this is like a flat surface, or even if it's got some thickness to it, on the other side of it is also going to be acting PATM. And if we think about this surface like this, if we just sort of break up this surface, what happens is this. All right, the pressure on the surface looks something like this. Okay. Here is PATM. All right, and then here is rho GHC, or rho GH. Oop. Right? Rho GH. So you can see that it gets bigger as it goes down. On the other side of the surface, we also have PATM. Right? And so the two PATMs are acting in equal but opposite directions, and so typically what we simplify the force on it is to equal this. Instead of that PATM, we say rho GHC, which is still the pressure at the centroid, times the area, okay? And that is essentially the force on a planar submerged surface. It is the pressure at the centroid times the area of my shape, okay? And it can be an arbitrary shape, all right? And we have to remember that to find the centroid, we would use this integral here. And I'll do another video a little bit more about these integrals. All right. So the next question is, where does it act? All right. So this gets a little tricky. Again, I'm going to draw, here's our surface. And remember that the distribution of pressure looks something like this. All right. Why does it look like this? All right. Because it gets bigger, right? Hydrostatic pressure gets bigger as we go down. We now know what the magnitude of this force is. It's rho GHC times our area. But ideally what we'd like to say is, where does it act, all right? So remembering that this is our downward direction, if we were going to balance this force, we'd want to say there's some force resultant, all right, that should balance this. And so we know that the force resultant should have what? It should have the exact same magnitude. It should be equal to rho GHCA, and that would mean that the sum of forces, let's call this direction W. All right, so the sum of forces in the W direction to equal 0 means that rho GHC minus rho GHC times A plus FRN has to equal 0, and so you could prove that. But we also might be concerned about the sum of the moments about our origin, where this point here is our origin right here, all right? And then how would we figure that out? Well, we might say something to the effect of this. We would say this has to be 0 if this is an equilibrium. And so what we're going to say is there's some distance here, which we will call y, and for now I'm going to call it CP. We'll talk about y in a second. And I'll say that force R times YCP, all right? And, you know, we would use the right-hand rule, so let's say into the table is positive, all right? Should be balanced by what? Well, it should be balanced by the moment caused by the pressure above. Now, the moment caused by the pressure above is harder to figure out, but if we think about just a little sliver right here at some arbitrary distance y, then there would be the pressure at y times the differential area times y. Okay? And so what we would say is, if we came back through now and said, all right, that our resultant force times YCP should equal, and this is the incremental, right? So this would be the integral over what? The integral over my surface. All right? So FRN times YCP would equal the integral over my surface PY times Y dA. All right? Now, we know, for instance, this, all right, we can now take this and say, well, what is Py? This is equal to the integral of rho g hc y dA. But we actually know that hc is related to y and sine alpha, right? So we could actually change this to y squared sine alpha. All right? We know that this is still ycp over here. And we also know that this is rho v hc, right? Okay, so let's keep simplifying. So now we can say that ycp equals the rho g's are going to cancel, right? And the sine alpha is going to come out, so we have rho g, sorry, equals, here we go, sine alpha over hc times the integral of y squared dA. Now this is a special integral. It's what we call Ixx. It's the second moment of inertia around the x-axis. It's sort of like a centroid to the next level. All right. Now sine alpha over hc. Oh, and I forgot there's a over here. There's an a over here. All right. We can rewrite this in a number of ways, but the easiest thing to do is to write it like this. So this is that ycp equals Ixx over yc times a. All right. All right. So ycp, actually CP stands for the center of pressure, okay? And it is equivalent to Ixx, the second moment of inertia, okay, divided by yc over a. Note, the origin for all of this is this point up here. I'll circle it up here again, right? It's the top of the surface where the fluid meets the solid surface, right? So everything is being measured in a positive direction down the surface, all right? So the ycp you calculate is going to actually be this value. Now it's important to realize that the ycp, the center of pressure, is deeper than yc. Why is that? The force, the resultant force, is going to act at a lower value, all right, than the than the centroid, because pressure gets deeper as I go along. All right, so if I wanted to simplify this, and I was going to say, okay, here's my solid surface, here's my flat thing, and I had this arbitrary shape, on it, I would say that there's a resultant force, Fr, which is equal to rho g hc times A. It acts at a position ycp, which is equal to Ixx over yca, all right, where Ixx equals the integral y squared dA, okay? And that Ixx is, as we've written it, okay, is measured from this point. Everything is being measured from this point, which is my origin, okay? Now, that is the main set of formulas you need to calculate what the force is on a flat surface and where it acts. And the things we need to remember are that the force is the pressure at the centroid times the area. 2, the centroid, yc, is equal to 1 over the area times the integral of y dA. 3, the force acts at the center of pressure, which is deeper than yc, and is equal to ycp, which is equal to Ixx over yca. When measured from an origin, all of these formulas I'm assuming the origin is being measured from that point. All right?